So we're going to talk algebra review. We're going to review radicals, going back to Algebra 1 and some things that we mastered hopefully back then. Hopefully today will be much of a review as we look at the radical stuff and working through here. But two rules from algebra. When you multiply numbers with the same base, the rule says you add the exponents. So that was our first rule from Algebra 1 that we're going to bring back today. And so our example over here on the left, or from the left, is x to the third times x to the fifth. We add those together is x to the eighth. Very straightforward. This is a normal rule from Algebra 1, just as review. The other rule from Algebra 1 that we're going to bring back today is when you have what's called a power to a power. And that means you take everything inside the parentheses and you raise it to that power. So here we have this example over here to the right. That means we're going to have 3 cubed and x squared cubed. So we have two parts there. Good morning, Kent. And so each of those two parts we're going to cube. So 3 cubed, as you know, is 27. And x squared cubed, there we have a power to a power. So our example there means we raise that to the 6th. So really straightforward, those two simple examples. As we review those basic algebra principles, we're going to be weaving those in and making the assumption that we have those pretty solid in our knowledge base moving forward. But I opted to take today and use today to really try to make sure that we were moving in a solid path on Algebra 1 for reviewing radicals, square roots, and things like that before we jump into section 7.1 tomorrow. So let's do a little review. This goes back to when we remembered our perfect squares. So let's see how many we can remember and how high we can go without our calculator. Okay? Everybody together. 1 squared is? 2 squared is? 3 squared? 4. 5 squared? 6 squared? 7 squared? 8 squared. No calculators now. 9 squared. 10. 11 squared. 12. Okay. 13. 169. I heard some faltering there. All right. Now 14 squared. What's the deal? Remember, you take the 169 and switch it. 196. 15 squared. 225. No calculators now. 16 squared. Take the numbers from 15 squared, which are the 25. And what is 6 times 6? So it ends in a 6. 256. 17, 18, and 19 all have the same pattern. What is 7 times 4? 28. What is 7 squared? 49, so it is 289. What is 8 times 4? 32. What is 8 squared? 64. So it ends in a 4, so it's 324. This only works for 17, 18, and 19. What is 9 times 4? 36. What is 9 squared? 81, so it ends in a 1, so 361. So that's just a little pattern for 17, 18, and 19 to help you remember those. The way I remember it is 7 squared is 49. So there's the 4 to get you going. So then 4 times the 7 is the 28. And lastly, what's 20 squared? 400. Okay. The expectation is that you know those perfect squares up through 20. Okay? That is the simple expectation. Now, let's go to cubes. No, we're not going to go to cubes yet. We're going to go to cubes tomorrow. Let's do some variables. Obviously, what are our perfect square variables? We have x squared. We have x to the 4th. We have x to the 6th. We have x to the 8th. We have x to the 10th. We have x to the 12th. Now, what squared equals x to the 12th? What do you have to square to get x to the 12th? X to the 6th. What do you have to square to get x to the 10th? X to the 5th. And x to the 4th, etc. And that is using the rule of the power to a power. So all your even exponents are perfect squares of your variables. Now, we use all these then to find and reduce our radicals. So let's look at some examples. There's two ways to do this. My hope is that you will learn and master the second method, but if you didn't, you could always go back to what we call prime factors. If we take 8 and break 8 down into prime factors, we get 2 times 2 times 2. Do we agree? So we would take those and we would group them in pairs. So there's a pair of 2s. The pair of 2s comes out as a single 2, and so we get 2 root 2. If we break down 98 into prime factors, well, 2 times 49 is 98, and 49 is 7 times 7. We take out the pair of 7s, and so the pair of 7s comes out as a single 7, and that leaves us an answer of 14 times the square root of 2. So a pair of numbers comes out as a single number in prime factorization. Now, the prime factorization method is nice, but it's a little bit slow unless you start to recognize stuff. So my hope for you is that you'll begin to be able to look at our problems and say, hey, we need to break these down into a perfect square times what is left over. And this method, I think, is going to help you tremendously as you go. So the perfect square that goes into 8, obviously, is 4. What's left over is 2. And so you guys know that means that's 2 squared to 2. The perfect square that goes into 98 is 49. What's left over is 2. So the square root of 49 is 7. So you get 14 root 2. Now, obviously with these two situations, it's not quite as advanced, but when we're dealing with radicals, it's really easy to deal with those perfect squares and try to extract them to make your life easier. The bigger your perfect square that you pull out, the less work you'll have to do. For example, the number, if we were breaking down a larger number, say 32, okay? 4 goes into 32, that's a perfect square, and also 16. You're better off going with the 16 and only having to do the problem once versus having to do reducing it twice. Or that's a question.
Are we allowed to use our calculator on the homework?
Yes, some calculators will reduce square roots, but there will be sections on the quiz that you will be allowed to use your calculator, so make sure you can do it without a calculator in practice. So let's look down at some examples here. I'm starting off with radicals of variables, just because I think it's a little bit easier. When you are taking the square root of a radical with variables, basically you're going to put a little note to yourself, cut the exponent in 2 or in half. Now, back in Algebra 1, you didn't really learn the y. I want to teach you the y. A square root of any number is really that number raised to the exponent of 1/2. So if you have your calculators, take them out, and I just want to show you this on your calculator very simply. And I want you to take a very normal square root. So we're just going to show you how this works and show you that actually it is a power of 1/2. So we're going to take a normal square root, all right, so what's an easy number to take a square root of? 25, right? 25 raised to the power of 1/2. So parentheses 1 divided by 2. So what should that equal? It should equal 5. Okay? If you want to instead raise it to the 0.5, you can also do that. Also is 1/2. So sometimes when you're taking square roots, it's a whole lot easier to raise something to the 0.5 instead of finding the square root button and doing all that. But here's the thing. Remember, when we're talking about square roots, the rule up very at the top that says a power to a power. And that's why you're multiplying effectively by 1/2. And so let's come back down here and look at this example. The square root of x to the 6th, well, you cut the 6 in 1/2, so that is just merely x cubed. Because x cubed times x cubed equals x to the 6th. And that's the whys behind it that we really didn't learn in Algebra 1. Over here, you could obviously realize that this is the square root of x cubed squared, which is also x cubed. So if you can just remember, cut the exponent in half when it's even. That really helps you. When it's odd, we're going to have to deal with it in a little bit different way. And that's what I have on example D down below. Example D, we have prime factors on the left. We're going to do that first. So let's break this down into prime factors. What does 75 break down into? What times what?
25 and 3.
25 and 3. And then we have x to the 5th and y to the 4th. And theoretically, you would say that's 5 times 3. 1, 2, 3, 4, 5. 1, 2, 3, 4. And this is what prime factorization really is. You stretch the whole thing out and write it as tiny little factors. Now I'm going to circle my pairs. There's a pair, there's a pair, there's a pair, there's a pair, and there's a pair. Each pair comes out as a single idea. So the 5s come out as 1, 5. I have 2 x's, so that's x squared, and I have 2 y's, that's y squared. What's not circled? A 3. What else? An x. So that's what's left inside. That's the long way. The nice thing, unit, it always works. The drawback, you have to write out that prime factorization and circle all your pairs. Now let's look at more of a suggested way as we're moving in here to Algebra 2. Let's break this down into perfect squares and what's left over. So we're going to write 2 radicals. Paul already told us that 25 times 3 is 75. I like the 25 because 25 is a perfect square. Is x to the 4th a perfect square? You bet, it's even. What's left over? A single x. Is y to the 4th a perfect square? You bet. So y to the 4th is up front. There's nothing left over. So I can get rid of the back end of my square root here. All right, so let's take the square root. The square root of 25 is 5. Cut x to the 4th in half. Cut y to the 4th in half. And what's left over? So you have 2 different methods here. Prime factorization, stretch it out, circle your pairs, or perfect squares times what is left over. My hope is you will begin to move towards the perfect square method as we are starting to be more on the Algebra 2 level versus the Algebra 1 level. I'm going to teach us in Algebra 1 in a chapter or 2, and they're going to be sticking pretty much over here on the left as they're working with prime factorization. And towards the end of the chapter, we'll start to jump them to perfect squares. Let's look down here at the square root of 8. Let's change this. Give me another even number. Larger. 60. Square root of 60. Let's change these. Break down 60. 2 times what? 30. And 30 is what? 2 times 15, right? And 15 is 3 times 5. How many pairs? Just 1. So what's my answer? 2 times the square root of 15. Or you can think, hey, does a perfect square go into 60? It does. 4 times 15, so 2 times the square root of 15. So either method is going to be very straightforward as you work through these. All right, let's take F and change this one up a little bit because it looks like it was the same problem. I'm not sure how that got duplicated. Let's go the square root of 80 x to the 9th y cubed. The square root of 80 x to the 9th y cubed. All right, let's break down 80. 2 times 40, right? And 40 is 2 times 20, and 20 is 2 times 10, and 10 is 2 times 5. X to the 9th. 1, 2, 3, 4, 5, 6, 7, 8, 9. Y to the 3rd. 1, 2, 3. I don't have room for it all. Let's circle our pairs. There's a pair of 2's. There's another pair of 2's. Circle our pairs of x's. 1, 2, 3, 4, and our pair of y's. So everything that's circled is going to come out. How many 2's come out? 2 of them, so that's 4. How many x's come out? 4. And how many y's come out? Just 1. What's left inside? It's not circled. 5xy. I'm not really wild about the prime factorization method. It seems like it takes a long time. Let's look at the perfect square method. If I was looking at 80, you get good at thinking, hey, 16 times 5 is 80. X to the 8th is the even number right below 9. So x to the 8th times what's left over. And y squared is the even number right below 3. So you have 1 y left over. And now we just take the square root. The square root of 16 is 4. Cut 8 in half. Cut 2 in half. And what is left over is 5xy. So there's a little bit of practice of mental math here, knowing your perfect squares, knowing what goes into things. But my hope is you're going to start to see those numbers and how they jump into these square roots very quickly, to reduce these things extremely fast, to make this very, very straightforward. The important thing is we're looking for pairs with square roots. Tomorrow we're going to jump to cubes. And if we're looking for pairs with square roots, what are we going to look for with cubes? 3. Okay, not pairs, but we're going to look for triples. And so it's a very similar idea tomorrow, but for today we're just going to stick in our intro stuff and review. So we're on page 362, which is in front of 7.1. It's kind of a lead-in section, and I've got it sitting down here for you. Very straightforward. A lot of them talks about powers to 0. There's one problem there, number 7. Just a reminder, anything to the 0 is 1. So I don't know if you need to remember that idea. Put it maybe at the very, very top. Anything to the 0 is 1. Just as a reminder there. Also, you guys know by now, anything to a negative is 1 over that to the positive. You know, some of those orders and rules of exponents. Okay?